So we're gonna practice using these. I'm gonna just throw some examples at you, see what's given to us in the problem, which equation to use, and go from there, because the difficult part is knowing which one to use. So the first example, let's say you drive in a car here. So last time, here is a car. What kind of a car? All my cars look the same. There's a guy driving the car. There's a hat. Here we go. See, that's how you know I draw a young man or a lady there. The long hair is the lady, the hat is the man. Driving the car in this direction, and I'll have fun with it. Let's say at 50 miles per hour, because you have to do conversion now. Suddenly you look, and there's a deer in the road. And you know, deer, they said, like a deer in a headlight. Once you see the headlight, they freeze. So here's a deer. I got to draw an animal now. All my animals look the same. They all look pregnant. They all look, God knows what. That's a deer. There's the antlers. I don't know. Any four-legged animal is going to look the same. They all look like that. Cat look the same. Dogs look the same. They all look the same. Okay, so it doesn't want to kill the deer. You feel bad there. You apply the brakes. This particular car has an acceleration and deceleration at the rate of 3.8 meters per second. So when you floor it, increase the speed at this rate. When you slam on the brake, it decreases the speed at that rate. Let's assume the deer is only 20, well, let's more than 20. Let's use 30 yards away. I'm trying to put crazy units in the problem intentionally. And the question, if you apply the brakes and you have that distance, the deer is 30 yards away, are you going to hit the deer? Is the car going to stop before it hits the deer? I don't know. We have to do the math. So let's find out how long would it take the car to come to a complete stop, distance-wise. Is it going to take the 30 yards? Is it going to take less than that? Velocity is going to mean stopping. And if it's more than 30 yards, you kill that deer, or you hit it. If it's under 30 yards, the deer is safe. So let's look and see what we know. Again, all we know the deer is 30 yards away. I don't care about that. I want to know how long, distance-wise, would it take the car to come to a complete stop. And if that distance is less than 30 yards, the deer is safe. If it's more than 30 yards, you hit it. So what do we know? We know the initial velocity, which is what? 50 miles per hour. Well, that doesn't help me. I need to convert that. So that's over 1. To convert from miles per hour to meters per second, what do? 1 meter per second, I think on that cheat sheet I gave you yesterday, is it 2.24? Might be 2.24 miles per hour.
Yes.
Is it?
Yes.
So let's see, 50 divided by, it's 22.3 meter per second. We know the final velocity is what? 0. The car is going to come to a complete stop. Am I slowing down or picking up speed? So your acceleration is going to be what? Negative 3.8 meters per second squared. And again, this is when you apply the brake, right there. You saw the deer, you hit the brake. So your initial position will say that's 0. when you apply the brake. From this point, where are you going to stop? How long is it going to take the car to stop? So what's x0, 0? What's x final is going to be? By the way, let's convert the 30 yards to meters, so when we get the answer, we'll know if you hit the deer or not. Where is that conversion sheet? Yard to meters, what's 30 yard? One yard is how many meters? 0.94, something like this? Or 1 meter equals what? Do we have that? Yard to meter. Nothing yet?
You have the conversion from meter to feet, and then you can...
Okay, we can go yard to feet. And feet to, so here we go. Let's go yard to feet first, right? 1 yard is how many feet? 3. So that's 90 feet. That's over 1. Now let's go from feet to meters. 1 meter is how many feet? Or 1 foot?
39 point.
1 foot would be 0.305.
0.305 meters? Yeah, 1 foot.
Yep.
So 90 times 0.305 is 27.45 meters. So when I find how long it takes the car to stop, distance-wise, because how long means could be time, but distance, if that distance is less than 27.45 meters, the deer is safe. If it's more than 27.45, we hit it. We get a dinner. Ooh, that's mean. I don't eat that stuff. Now let's see which equation. So again, let's summarize what we know. Clean sheet of paper. We have the initial velocity, which is 22.3. We have the final velocity, which is 0. We have the acceleration, which is negative 3.8 meters per second squared. Initial velocity is 0. We're looking for a final position before the car comes to a complete stop. Which equation out of these has the minute? Let me put the equations right here. Let's look at these equations. Which one has all these pieces in it? To me, it looks like the fourth one, doesn't it? It has x, we're looking for x, you know x of 0, you know v0, you know t, you know accelerate, well, we don't know the time, right? No, I can't use that. How about number 5, the bottom one? I know this, I know this, I know the acceleration, I know the initial one. The only thing that's left is x. I couldn't use this one. I start by saying, let's use this one. I'm looking for this, so I'm looking for it. I have this, I have this, I have this, I have this. But wait a minute, I don't know what t is, right? So I'll have 2 unknowns. You can't solve an equation that has 2 unknowns in it. So that's why I couldn't do this one. This one, could I have done this? Well, I don't know what t is. I really could have found t from this and plug it right here, too. I can use sometimes 2 equations. But this will take me there in 1 step. So v squared equals v0 squared plus 2a times x minus x of 0. Final velocity is 0. Squared still 0. 22.3 squared. 2 times a negative 3.8. X minus 0. Zero equals, let's take the calculator here, 22.3 squared. 497.3 minus 7.6x. If you take the 7.6x to this side, it turns to positive. Can we get what x is? 497 divided by 7.6, which is 497.3 divided by 7.6. It's 65. That deer is history. It's going to take the car 65.43 meters to stop, and the deer is only 27 meters away from us. You're going to hit it. As I said before, you don't have to use that equation. I could have used two equations, put them together. Watch this. Because my first reaction was use one of these. I know V initial, I know V final, I just didn't know what the time is. So I could have used the top equation to give me the time. Notice if I use the top equation, V final is what? 0. V initial 22.3. Acceleration is what? Negative 3.8 times time. 3.8 t equals 22.3. Can I get the time? It's 5.87 seconds. So I could have took two equations, put them together to get the same answer. Now, once I know that, use the third equation. I'm looking for x. Use that one. I'm looking for x. I know this is 0. 1/2 v0, the initial velocity is what? 22.3 plus 0 times the time, which is I just found 5.87. Does it show up there? Yep. .5 times 22.3 times 5.87, and it is 65.45 meters. Again, the difference of 200th of a meter is rounding errors. So it's the same answer. It's going to be 65.4 meters before we, come to a complete stop. You can do it in one equation. You can do it in two equations. Solve for t in one, then plug into the other one. Let's try another example. Okay. You're driving down the street and the speed limit says, here we go, speed limit. "25 miles per hour." There's a sign in the ground. But you're not paying attention to that sign. So you're in your car, you got a red Ferrari, a red new, giving you a new car here, a nice car. Nice sporty looking car, here we go. And you're going 40 miles per hour in a 25 mile per hour zone. Now here's the bad news. we got a police car on the side here with the radar pointing at you, and they see you speeding. Here's the police car, black car. Usually most police cars are black. The minute you go by them, parked on the side, here goes the siren. We'll put the red color, the light. Oop. Now you're in trouble. The siren goes off. There's a driver in the car. It's amazing, we can see their legs in the car too. Looks like made out of glass. So the police car sees you, this could be a state police, whatever. Now you decided, you know what? You didn't even notice that. You continue moving at constant speed. You stayed at 40 miles per hour the whole time. Now the police car was parked, so has initial velocity of what? 0. He sees you, puts the siren on, hit the gas pedal. The acceleration on that car, on the cruiser, is 4.5 meters per second squared. And now he's driving, let's say the two roads side by side, it's better to see it that way. And the question is, you halfway through the trip, you're going to be ahead of the cruiser because it's going to take the cruiser a little bit longer. And the cruiser is going to be right there, still coming with the lights on. All these colors I got to switch. Then eventually you're going to reach this point where the two cars are next to each other. And there's the cruiser. So how long it takes the cruiser to catch up to you? So now when the cruiser catches up to you, you drove the same distance. Both cars, from that time, from this point on, you drove the same distance and the same time. You go by him, turns the siren, start to go. The time it took this car to go from here to there is the same time it took the police car to go from here to there. It's the same distance too. So how long does it take him, time-wise? How far? We're looking for that. Let's ask for this question. What is the time it's going to take for the cruiser to catch up to you? I don't even know anyone in Phoenix. So we're looking for that. We're also looking for the distance. How far before the cruiser catches up to you? And what is remember, you never change your speed. For some reason, you did not even see the police officer. You had the cruise control set up at 40. It's 2 lanes, side by side. You're in one lane, he's in the other lane. You still didn't see him. The light, the flicker, and the siren. You get your earbuds in, you're listening to music. Maybe DJ Cool or some, I don't know, who's popular? Justin Bieber playing music. I like Justin Bieber, actually. I do like his music. My mama doesn't like you. I like that song. And the other one, what's the found velocity of the car, the police car, when they catch up to you? 3 questions. Okay. Let's label the cars. Car 1, car 2, police car, you. So this is you. This is police car. Let's write what we know about each one. For you, what was your initial velocity? 40 miles per hour, right? Let's convert that to meters per second. Divided by 2.24. 40 divided by 2.24. 17.86. meters per second. What's your final velocity? Same thing. That's you. It says constant speed. You never slowed down, never touched the brake. You had the cruise control set up. What's your acceleration? For you.
The same number?
Think again. 0. Why 0?
Because you're going at a constant speed.
Yep, but acceleration is change in velocity over change in time. Remember acceleration? Final velocity minus the initial velocity divided by the time. Your final initial velocity are the same. There is no change in them. So your acceleration is 0. For the police car, what was the initial speed for them? 0. What's the acceleration for them? 4.5. What's the final velocity for the police car? Unknown. Do we know anything else? Okay. Which question you want to answer first? You want to answer the time? You want to answer the x? Let's look at the time. Let's answer that one first. And the time here is going to be the same. So if I know the time from this, I know the time for your car, the police car. So let's look at u here. We have the initial velocity, the final velocity, the acceleration. Can we get the time? Let's plug it in. Well, when the acceleration is 0, we got a problem. When the acceleration is 0, if you put acceleration is 0, this is gone. It says, oh, final velocity equals initial velocity. Well, I know that. So I can't use that equation. I can find the average velocity. Well, if you go on a constant speed, what's your average velocity? If you go on a constant speed, what's your average velocity? Let me ask the question again. Take this example. It says average velocity or speed is the initial plus the final divided by 2. What was your initial speed for you? 40 miles per hour. What's your final speed? 40 miles per hour. When you add them, what do you have? 80 divided by 2, what do you have? 40. It better be the same. You're going at constant speed. That's your average speed. That's your final speed. That's your initial speed. That's your instantaneous speed. I don't know the distance. There's too many unknowns. I can't find x's. I don't know what t is. We know the acceleration is 0. We don't know time. We don't know distance. So it seems like to find the time is going to be difficult because I don't have a lot of stuff there. Same thing right here. I only have initial velocity, final velocity, acceleration. I don't even know what the final velocity. I wonder if I should find the distance first then. Let's see if that will help me, if I can look for the distance. Or maybe the time, I don't know. If I plug one of these equations, just too many, seems like too many unknowns, but I can get an equation from here and I can get an equation from here. If you have two equations by two unknowns, could you solve them? Sure we can. So let's look and see. Let's write some equations, see if that'll help us. This is not an easy problem, so you got to think about this a little bit. Let's take, I don't know, Let me take for u here. Let's try this equation. That's for u. We have x equals x sub 0 plus 1/2 v0 plus v times t. We're not sure what x is. We're looking for it. That was one of the questions. $17.86 plus 17.86 times t. It says x equals, if you do the math, 17.86 times t. I can't solve it. Two unknowns in that equation. Let's look at the police car. I need another equation that has this information in it. I got to make sure I have x and t in it. Well, I can't use this equation, same one, because if I use the same one, I don't know this one. I have no idea what the final velocity for the police car. So I'm going to have three unknowns. That won't help me. What about this one? If I use that one, I should have waited on this problem for a few more minutes. Let's write what do we know about the police car. Do we know the initial velocity? Yes, that's 0. 0 times the time, which is 0, plus 1/2. We know the acceleration for the police car, which is what? 4.5 times what? T, which is unknown, t squared. Do the math. And what do you know? We got two equations by two unknowns. And now we need to solve them. We can use substitution from algebra. You know what x is equal to, 17.86t. Plug it in here. So take this equation now and replace x with 17.86t equals 2.25 t squared. Can we solve that equation now? We can move this one here. We can factor a t out. And if you remember from math, when you're multiplying two things, your answer is 0. That means one of them has to be 0. So t could be 0, which is true. Why is t 0? That's when you go by the police car. Travel by the police car, time is 0 now. So at that time, oh yeah, they have the same time, the same distance. Also down here, let's see how long it's going to take them to catch up to you. So the second one is 0 now. Bring the 17.x to this side. Divide both sides by 2.25. It's going to be 7.94 seconds. So time-wise, how long is it going to take the police car to catch up to you? 7.94 seconds. If you know what the time is, you can use either one of these equations now to get the distance. What's the distance? Either one, that looks like easier to use. .86 times 7.94. Distance-wise, going to be 141.8 meters. Roughly, I don't know, 170 maybe yards. Almost, it's not really, football field is 100 yard. A little bit less than 2 football fields. So this is the time. How long is it going to take the police car to catch up to you? This is the distance. How far is it going to take them to catch up to you? 141 meters. Can we find now what the speed of the police car when they caught up to you? Now let's go back to the police car. What do we know? Now we know X and we know T. That's correct. We know X to be what? 141.8 meters. We know the time. Oh, that's X, right? We know the time, which is what? 7.94 seconds. So if you plug them in, we can use any equation now. I can use V equals V0 plus AT. Initial velocity of this car was 0. Acceleration is 4.5. And the time is what? 7.94. .5 times 7.94 equals 35.73. That's meters per second. And if you want in terms of miles per hour to see how fast the cop is going, you should ticket him too. Because the speed limit is what? 40 in the 25 on that road? Wait till you see how fast he's going. One meter per second is equal to 2.24 miles per hour. So he's going at 80 miles per hour, trying to catch up to you. Or when he catches up to you or she catches up to you, the police car is moving at a speed of 80 miles per hour in a 25 mile per hour zone with little kids running around. You know. Make a citizen arrest. That was a tough one. I should have waited a few minutes on it. I'll make one, maybe not as tough as that. I'll make my own. Let's say you come into land, there's the plane, about to land. When you land, you tip that nose up there a little bit. So the plane comes to land. Usually when you fly in commercial plane, when they land, they're moving about 130 miles per hour when they hit the runway. That's the same speed the plane takes off. So try to hit the runway with the same speed it takes off. In case there's a problem, they can just give it power and continue taking off again. Now the plane now parked here on the runway. And final velocity is 0. Next time you fly, if you stand by the window, you look at the runway, you'll see numbers 1, 2, 3, 4, 5, 6. There's actually how many miles, how many thousand feet left on the runway. So as the pilot goes by them, he knows when he's landing, he'll say 7, 6, 5, 4, 3, 2, 1 to give him an indication the runway is going to end soon. If you're going too fast, are you going to make it or not? But let's say the plane lands in 3,000 feet. It took the plane to land. We need to change all the units in a minute there. Let's find out how long it takes the plane to land from the time it touches the ground to complete stop. Let's also find out what the acceleration of that plane, which should be a negative number because you're slowing down. Two things. I gave you all the numbers in different units intentionally to practice unit conversion, because that's what you're going to see in real life. You don't see meters per second, miles per hour, feet. So let's convert that. From miles per hour to meters per second, you divide by 2.24. So the plane is going at 58.0 meters per second. 3,000 feet. How many meters? Somebody just told me 1 foot is, what was it, 0.309 or something? .305. So it's going to be 915 meters. 9.5 football fields before the plane comes to a complete stop. So this is what we know. We know the initial velocity of the plane, 58. We know the distance, the change in x, that's the final minus the initial, the change. If I use this as the initial, this is the final. The change in that is 915. Which means the initial is 0, the final is 915. What else do we know? We know the final velocity of the plane when it comes to a complete stop is what? 0. And we're looking for the time. Again, let's put that cheat sheet here. Do we have an equation that can be used here?
The first one, right?
Well, if I'm looking for the acceleration or the time, yeah, if I'm looking for the time, I could use this first one, correct. Well, wait a minute. Yes, we can find the acceleration. Looking for the acceleration first? Okay. I was looking for the time first. If you can do the time, you can't because you don't know what the acceleration, right? But if you're looking for the acceleration, you still can't use it because you don't know what the time is, right? Too many unknowns. You don't know the acceleration all the time, so you can't use the first one. I'm not a fan of these two, but I mean, you can use them. Let's go to this. Do we know the initial velocity? Position, final position, initial velocity. Two unknowns, what? The time and the acceleration. What about this one? Oh, I can find the acceleration on the last one. Can you see there's only one unknown in it? You can say v final squared equals v0 squared plus 2a x minus x sub 0. 0 squared, that's 0. 58 squared. 2 times a x, which is 915, minus x sub 0, which is 0. $58 squared is 3364. 2 times 915. 1830 times a. Bring that number to this side, becomes a negative. Can we solve for a? Notice it's negative. The acceleration is negative because the plane is slowing down. .84. meter per second squared. So the plane is slowing up at the rate of 1.84 meters per second every second. Now, if we know the acceleration, can we find the time? Now we can use the first equation. Okay, what's my V0? My V, actually, I know what V is. 0, right? My final velocity. What's my V0? 58. Plus the acceleration, negative 1.84 times the time. Now, the one little thing I'll point out to you, sometimes when I write negative 1.84, I'm really still carrying all the digits on my calculator, so my answer might look different than yours, because I get all these numbers here. So you bring it to this side, that's 1.84 t equals 58. And to get t, we take the 58 divided by that number. So I'm using 1.838 for that number. It's 31.55. 31.6 seconds. So it's going to take the plane roughly half a minute to come to a complete stop. Make sense? So that's how we do these problems. Sometimes you drop things, free fall. And when you drop things, I know I'm looking at time here, we're going to miss the lab today. We'll do it tomorrow morning, the first thing tomorrow, because I don't have enough time for it today. So I'll continue with this, try and finish the chapter. I'm almost done. With the free fall, when you drop something, once you let something go, it's coming down. Why is it coming down? Gravity. Gravity is pulling down on you. If we neglect the wind resistance, like you drop a piece of paper, notice it glides a little bit there. It's not as fast because the air is pushing up on it. But you drop a rock, you drop a pen, you drop something heavy, it goes down. Well, free fall, you know that the acceleration is down, and that's negative 9.8 meters per second squared. Even when you throw the pen upward, once it leaves your hand, the acceleration is pulling down on you, on that pen there, at the rate of 9.8 meters per second squared, always. I just want to see if our book uses negative for down. Where is it? I don't just want, it doesn't really make a difference, just don't want you to get confused which one's positive, which one's negative. I don't know, I'll just use up as positive, down as negative. All the equations that we did there, they're still good. All the ones we showed you, you just move in the y direction. So if you don't like to call it x, you can just change x to y because you're going up and down. That's the only difference, really. If that doesn't bother you, you just use x for the height. So just an example here. You don't like your physics teacher, so you sat on top of a building. Here's the building. Let's say you're on the 6th floor waiting for him to come out. The building is, I don't know, 50 meters high. And once you saw the teacher coming out, you had a water balloon in your hand. You don't want to kill the person. You just let it go. So you're holding the water balloon and you let it go. What's the initial speed of that water balloon? You're hoping to hit him on the head there. That's what your plan is. What's the initial speed? If you just hold it and you let it go. 0. Now, if you throw it down, then it has initial speed. If you throw it up, has initial speed. If you throw it up at the rate of 3, has a plus 3. If you throw it down at the rate of 5, has a negative 5 initial speed. Because I'm using up as positive, down as negative. And let's say this teacher is 2 meters tall. So the ball is not gonna, the water balloon is not gonna hit the ground. It's gonna hit the teacher on the head. So it's actually gonna travel how many meters, that water balloon? 48. So you can use reference anything you want to. If you use the head of the teacher as reference, right there. Let's see what we know. Do we know the initial height? X sub 0?
50 meters.
Well, if you're going to use this as reference.
Okay, sorry.
48. If you use the ground as reference, you're right. What's the final height if I use this as reference? 0. Again, I could have used the ground as reference, then the initial becomes what? 50, and the final becomes what? 2. Still 48, the gap, so it doesn't make any difference. We know the acceleration, which is what? Negative 9.8. We know the initial velocity is what? 0. Let me ask a couple of questions. How long would it take the water balloon to hit that teacher on the head? And how fast the water balloon is going to be coming down? My answer should be negative because it's moving which way, up or down, the water balloon when it hits him? Down should be negative. I can't use the first equation because I have 2 unknowns. V and T are unknown. I could use this one, right? I know everything except T. I know the initial, I know the final, I know the initial speed, I know the time. I'm looking for time. I know the acceleration. So I could use this one. What is my initial or my final height? 0. What's my initial? 48. What's my final initial velocity? 0. What's the time? Unknown. 1/2 negative 9.8 t squared. How many unknowns in that equation? 1. So 4.9 t squared equals 48. T squared equals what? Almost 10. 48 divided by 4.9. 9.8. Which means second squared here actually, because that's t squared. What's t equal to? The square root of that. Take the square root of that number. 3.13 seconds. So the balloon is going to be, or the water balloon is going to be in the air, coming down. It's going to take 3 seconds, a little bit more than 3.13 seconds before it hits that teacher on the head. Once you know the time, can you find how fast was it moving? I can use this. And it's going to be a negative. Negative to indicate it's coming down. It's the direction of it. Acceleration is what? Negative 9.8. The time is 3.13. It's going to be moving at good speed. 30.7 negative meters per second. It's going to hurt. That's 79 miles per hour. You know? Trust me, you'll feel it. You might have to go see a chiropractor after that. Especially if it weighs about a pound. Imagine a pound hitting you at a speed of 79 miles per hour. You won't be happy. Again, the negative indicates coming down. If the question, what's the speed? What do you do if it was, what's the speed? Take the absolute value of that number. Speed does not have a direction. The minus to indicate is coming down. If it says what's the speed, it's 30.7. Again, I could have used the ground as reference. I could have used the top as reference. If you throw it down, then the initial speed will be not 0, will be minus, let's say, 10 miles per hour. If you throw it upward, the initial speed will be what? Plus whatever the speed you throw it upward with. You know, I'm using up as positive, down as negative. And if I decide to make down positive, up negative, my answers will be exactly the same, except this will be a plus because I'm using down as positive, up as negative. But our book, I think, is using up as positive and down as negative. Yeah. Okay, I'll stop here. I tortured you long enough.